Now let us solve a problem. The problem is we have a bar of length 800 millimeters. This is fixed at one end and it is loaded at the other end with a force P is equal to 3 kilonewtons. What is given is the value of Young's modulus E is equal to 2 into 10 raised to 5 Newton per millimeter square, and the cross-sectional area A is equal to 300 millimeter square. What you need to find is the displacement values. The first step in solving the problem is to discretize the domain. So we will divide this bar into two elements with 3 nodes, and let us number the nodes as 1, 2 and 3. Displacement at the node 1 is u1, and the displacement at node 2 is u2, and the displacement at the node 3 is u3. Now if we see the condition at the boundary, at the node 1 we know it is fixed, so the displacement u1 is equal to 0. Since the total length is 800 millimeters, the length of each element is equal to 400 millimeters. If we draw the free body diagram by removing the support at the left, we know that there should be a support reaction R. Let the nodal forces be F1 at the node 1, F2 at the node 2 and F3 at the node 3. From the problem we can see that at node 3 the value of the force F3 is equal to 3 kilonewton, and there is no force at the node 2, so F2 is equal to 0, and at the node 1 the value of the force F1 is equal to R. The next step is to write the stiffness metrics for element 1 and element 2. This is the element 1 and this is the element 2. The stiffness metrics for element 1 is EA by L into 1 minus 1 minus 1 and 1. This equal to 2 into 10 raised to 5 into the area is 300 millimeter square divided by 400 millimeters, the length of the element, into 1 minus 1 minus 1 and 1. That is equal to 1.5 into 10 raised to 5 into 1 minus 1 minus 1 and 1. Now the stiffness matrix of element 2, again that is EA by L into 1 minus 1 minus 1 and 1, and the Young's modulus is 2 into 10 raised to 5, area is 300 millimeter square, and the length of the element is again 400 millimeters. So we get 1.5 into 10 raised to 5 into 1 minus 1 minus 1 and 1. Now we have to assemble the element stiffness matrices and obtain the global stiffness matrix. That is again EA by L into 1 minus 1 minus 1 1, and for the second one you add 1 here and then minus 1 and 1, 0 and 0 here, which will give you 1.5 into 10 raised to 5 into 1 minus 1 0 minus 1 1 plus 1 2 minus 1 0 minus 1 and 1. Now the global equation, that is K, that is the global stiffness matrix, into U, that is the global displacement vector, is equal to F, which is the global load vector. If we expand this, we get K is 1.5 into 10 raised to 5 into 1 minus 1 0 minus 1 2 minus 1 0 minus 1 1 into U, that would be U1, U2 and U3, that is equal to F, which is F1, F2 and F3. Next step is to apply the boundary condition and substitute the load values. We have U1 is equal to 0, U2 and U3 are the unknowns. In forces, we have the value of F1 is equal to the support reaction R, F2 is equal to 0 and F3 is equal to 3 kilonewton. Now to substitute the values, we know the value of U1 is equal to 0, we only have U2 and U3, and for the forces we have F1 is equal to R, F2 is equal to 0 and F3 is equal to 3 kilonewton. Now to solve this, first we see that the value of u1 is 0, which means the first terms or the first column values gets multiplied with 0. So you don't have to consider that at all, so you can cross the first column here. And second, the reason why f1 is equal to r is because you fix the node 1, or when you fix the node 1, u1 is equal to 0. So r actually is not an applied force, but a force which develops as a reaction because we have fixed that particular node. So the first equation does not help us in solving this, so we can cut the first row here. Now what remains is what is shown inside the yellow box, so we will write that below. Now we can write this as two equations. The first one would be 1.5 into 10 raised to 5 into 2u2 minus 1 into u3 is equal to 0. The second equation is 1.5 into 10 raised to 5 into minus 1 into u2 plus 1 into u3 is equal to 3 into 10 raised to 3. Now we can simplify these two equations and write them as, we can now write these two equations as 2u2 minus u3 is equal to 0, and the second one as minus u2 plus u3 is equal to 2 into 10 raised to minus 2. We can now solve these two simultaneous equations and find the values of u2 and u3. We can add these two equations. So the first equation will be 2u2 minus u2, that is u2, and minus u3 plus u3, they cancel each other. So u2 is equal to 0 plus 2 into 10 raised to minus 2, that is 2 into 10 raised to minus 2. To get the value of u3, we can substitute the value of u2 in the first equation. So what we get is 2 into u2, which is 2 into 10 raised to minus 2, minus u3 is equal to 0, which will give you the value of u3 is equal to 2 into 2, that is 4 into 10 raised to minus 2. The units are in millimeters. We have finally solved the problem, and the values of the nodal displacements are u2 is equal to 2 into 10 raised to minus 2 millimeters, and u3 is equal to 4 into 10 raised to minus 2 millimeters. These are nodal displacements.